Okay, thank everyone for being here. It's a true delight for me to introduce today's speaker in the De Giorgi colloquium, Professor Andrew Wathen, or Andy, as I've always known him. So Andy is a leading figure in the field of numerical methods for PDEs and algorithms and iterative methods and preconditioning for problems, especially from fluid flow, but also in optimization and especially problems from optimization problems where the constraints are expressed by partial differential equations. So Andy has also worked on a variety of other topics, including Toeplitz solvers, but also interesting applications such as how the butterfly gets its colors and patterns on its wings. I've always been fascinated by this aspect, little known, perhaps, not as well known, perhaps, aspect of Andy's activity, at least in the numerical analysis community. He's also worked on, I noticed, on problems of epidemiology and other aspects of applied mathematics. So Andy's been at Oxford since 1996. He belongs to New College. It's called New because it was founded in 1379 in opposition to Oriel College, which he attended as an undergraduate. I was a member, a fellow, how do you call a student, undergraduate student, which goes back to 1324, I believe, or something like that. Yeah. So as a tutor in the college, he has to tutor his students in many aspects of applied mathematics well beyond numerical analysis, things like magnetism or relativity, which is quite different, I think, from the system we're used to. And anyway, so I don't want to take any more time from Andy's presentation. Andy gives very stimulating talks. Certainly his work has been an inspiration for many of us, and in particular for my own research work. So without further ado, Andy, please.
Thank you, Taylor. Thank you very much for those very gracious words. I think too gracious. I do teach various things. I even teach calculus of variations, which I wouldn't dare dream of mentioning in this audience of experts and so on. But let me thank Andrea for the arrangements for this particular De Giorgi seminar. You'll see that I'm not an analyst, but it's a great privilege to speak in a colloquium named after one of the great analysts, I guess, and it's a real privilege to be here. We all stand on the shoulders of giants, and those of us who work in trying to solve problems in practical ways and so on, we fortunately have analysts to guide us to the problems that are worth solving. I mean, that's you know, really the nature of it. So I'm delighted to be able to give this De Giorgi colloquium here in one of the great academies of Europe. So I thought I would talk about some aspect of my work that has intrigued me for quite a long time. And it sort of arose out of the fact that I started off as a young man interested in solving differential equations, partial differential equations with numerical methods. And as I got a little older, I realized that, well, people don't always just want to know the solution of a differential equation. They sometimes want that solution because they're trying to design something. They're trying to design a wind turbine or an aerodynamic device or something. And they really want to do it in such a way that they achieve some optimality, some character that is so best possible in amongst that. So let me kick off. The thanks are to some of my former collaborators who were involved in this work. You can read the names here. So let me start off with a very simple thing. I hope that if we start off and think about a optimality problem where we're simply trying to have a quadratic cost function. I don't know. Do I press on this arrow here? Okay, is that better? Anyway, that's better. Okay. So here's a simple quadratic cost function. We think of A as being perhaps some kind of Hamiltonian or some kind of symmetric and positive definite or Hermitian positive definite operator. And we're not just interested in minimizing this quadratic function, but we have some side conditions. So when we're trying to divide we're trying to optimize, we have some constraints. And I've written them down here as linear constraints with some matrix B, which is generally non-square. Okay, so that, the way to solve such problems is well known, right? Right, though it seems as if I now have, oh no, I don't, it's just slow. Okay, the way to solve the problem is quite clear. I mean, this is due to Lagrange. I guess you build a Lagrangian by adding the constraint with some Lagrange multipliers. There's quantities I call lambda. And then you look for stationarity. It's the saddle point, but you look for conditions of stationarity for this Lagrangian, and necessarily they give you, well, the quadratic term becomes linear. This term becomes B transpose times lambda, and Bx equals C is obviously returned as the constraint. So in this very elemental structure, one gets what are these so-called saddle point problems. And the great paper on this is the paper due to Michele Benzi and Jean Golub and Jörg Gleason from 2005 in Acta Numerica, which is nearly 20 years old, but still contains a great deal of really relevant stuff. There is some stuff since then, but actually they did a really good job. So we have primal variables X and we have Lagrange multipliers lambda, and we're trying to, in general, solve these systems, which I always call curly A and Y and F is the right-hand side. So this is simplified, right? This is a quadratic cost function, and this is a linear constraint. And well, that's not so crazy because often that's what we do. We approximate things by polynomials or by low order models like this. So the classic problem of this type is really a problem of PDEs, I think, and that is the problem of incompressible viscous flow. And this is work of Irishman Stokes, where you minimize the viscous energy of an incompressible viscous fluid subject to its conservation of mass. So that's not always the way this problem is specified, but it's essentially what it is. And so you get this top equation, which is essentially the conservation of momentum equation. And then you get the conservation of mass, where here y is the velocity, p the pressure is the Lagrange multiplier, and u would be any body forces applied to the fluid, to the momentum equation. So you would think that this sort of problem would therefore give rise to these so-called saddle point systems, and with any kind of, most kinds of numerical approximation. I'm not going into absolute detail with this, but if you use finite elements or the so-called Mach finite difference approximation, then indeed this sort of problem yields a saddle point system of this type, where K essentially represents these terms, the viscous terms. So it represents discrete vector Laplacian. And you can see in 2 dimensions, it's just 2 copies of the Laplacian here. So this is one of the simple formulations of Stokes. So what I'm really interested in is, well, how do you solve these problems? Right? How do you solve these problems? You've got this saddle point matrix with these Laplace type operators K, and then these constraints B, which are sort of divergence. B is like the divergence, and B transpose therefore minus the gradient, basically, or the other way around. But to us in numerical linear algebra, this is just, well, generally large, because we tend to build, use many degrees of freedom. There's a large and sparse typically when we use finite difference, finite elements. It's symmetric, but it's indefinite. When you have a 0 entry on a diagonal, it must be an indefinite matrix. And so typically we would turn to so-called iterative solvers. That is, we would think that the work involved, we can estimate the work involved in doing direct calculations on this using Gauss eliminations and variants thereof. And it's typically infeasible on computers that we have today. So it's not a question of it would take too long. It would take longer than your lifetime for most of the problems that we do, even if you have the biggest computers, because the complexity is just too high. And so that's why, in particular, when we have 3-dimensional domains, we turn to iterative methods. And the one that's relevant in this context, and I'm not really going to mention any other iterative method in this talk, actually, is the so-called method of minres, which is due to Chris Page and Michael Saunders from 1975. And this is a so-called Krylov subspace method. That doesn't matter. All you need to know about it are these 2 green bullets. And that is that it's an iterative method. At each iteration, you need one matrix times vector multiplication with this matrix. If this matrix is sparse, then that means it has very many zeros. You can do this very quickly. And the convergence of that iteration depends only on the eigenvalues of this coefficient matrix. And so here's a typical convergence estimate. So R here is the residual. It's some measure of the mismatch between the iterate you have and the solution. And so the iterate at the kth stage, the residual at the kth stage relative to where you start, it's always good to start with a small residual if you can, which you don't always know. And this essentially is expressed in terms of polynomials. So this is the set of polynomials of degree k or less. This is just a normalizing factor to make sure you don't have a trivial problem. And this is just saying you want to minimize the maximum discrepancy of a polynomial at the eigenvalue set, at the spectrum of this operator. So it's real symmetric, so all the eigenvalues are real. It's indefinite, so some of them are negative and some of them are positive. But essentially, you want to find a polynomial of degree k at the kth iteration that is small at the eigenvalues. So if you have only 3 eigenvalues, then the right-hand side here is 0 when k equals 3, because you can choose that polynomial which is 0 at those 3 eigenvalues and is normalized at the origin. So what this tells you, I mean, this sort of estimate, which we're very used to in this sort of area, but I'm trying to give you a little intuition about it. It essentially tells you that if you have few eigenvalues or indeed clusters of eigenvalues, then you tend to get very rapid convergence of these iterations, and hence you can achieve these solutions which you couldn't achieve if you were trying to apply direct methods. Okay, so the snag is, of course, we can't determine the eigenvalues. We can't say, oh, let's just look at problems that have nice eigenvalues. So we have to turn problems into problems that do have nice eigenvalues if we want to get fast convergence. And this is achieved in almost all situations by so-called preconditioning. And I put in quotes here that we simply, for the same solution, apply an operator or a matrix P, which is some kind of approximation of the operator that we're interested in. And that preconditioner should achieve this fact that we do get few or clustered eigenvalues of this coefficient matrix. That will guarantee us fast convergence of this iterative method. And the other thing is, well, that sounds sort of, why don't we just use P equals A? That would, of course, have one eigenvalue, and that would be ideal. But of course, that's not sensible because we have to also solve systems with P at each iteration. A system, a linear system with P. So for a given R, we've got to determine Z for our preconditioner at each iteration. So we have this balance. Okay, and so to satisfy this second one, you might say, well, let's just choose P equals I. Okay, and then there's no work to be done here, Z equals R, but then it doesn't achieve this if A has rather spread eigenvalues. So there's always a, well, not always, I mean, but what we're trying to achieve is a balance between these two things. And actually, it's rather amazing how often that balance can really be struck with certain types of problems, and I shall show it to you here. Okay, so that's sort of the background of what I'm talking about. We're trying to solve systems that involve saddle points. We're going to use iterative methods. We want to find preconditioners that mean that we can get fast convergence and therefore solve these problems. So this is what my title expresses. That's what I'm going to really talk about. And that is about optimization with PDE constraints. So I'm not going to talk in general about this because I think it's too big, but I'm going to give you a certain type of sort of a type of problem which gives us some interesting things and is certainly useful in many contexts. So let's think of having a domain omega, could be an R2 or R3. This is the domain for a PDE. I'm going to be given a function y hat. I'm going to assume that's an L2 function. It could be smoother, but it's not really crucial here, actually. So y hat is some kind of desired state, right? And then I have a regularization. So there's a parameter here, beta, that's a regularization parameter. And I want to find y, which is close to y hat, my desired state. This is just in the L2 norm. I just chose this for simplicity. But it must be that y solves a differential equation where u is the forcing. So L here is just a differential operator. So we have here some physics. If you want to design a wind turbine, the physics is the flow of the air through this turbine. That's your physical constraint. And you want to optimize in terms of getting energy out of this turbine. If you want to design an aerodynamic structure, you typically want, for example, lift, and you want with acceptable, or minimize drag with acceptable lift, or something like this. That's your criterion. Slightly different problem, not formulated in this way. I've chosen that Y is the desired solution on the boundary. Just this is the boundary of the domain omega. But actually, we don't want to consider putting in too much energy here. That is, we don't want to specify U to too much precision. So this is the role of the regularization. We want to make these two things close, but we're not prepared to make U very, very large to achieve that. And so we also add this term where beta is positive, so that this penalizes against too much energy being put into this control problem, basically. But you see the minimization here is over both the state that solves this differential equation and U, the control. Right. So this is a so-called tracking PDE-constrained optimization problem. There are many generalizations of this type of problem. It could include actual bounds. These are pointwise bounds. This is rather awkward because you're dealing in Hilbert spaces, and now you've got things which are like pointwise. It's a very mismatch in some sense. But you sometimes have, we cannot make you go any bigger than something or smaller than something. That's just not possible. So when you're designing like a wave energy device, you cannot let the water overtop the barrage. It's an absolute constraint. We do this with a primal dual active set strategy. I'm not going to say anything about that. You don't need to know that, but it is a thing, and this is a relative reference, the important reference for this. Sometimes we have bounds on the state. The solution cannot be bigger pointwise than some upper or some lower bound. And here we have to do something really heavy duty. So we have to do Moro-Yoshida regularization, which again, I'm not going to talk about. But I'm just saying these are possibilities that you can actually do these things. As a nice paper by Herzog and Sachs as others. Very often you have boundary control. You can only control on the boundary and not in the domain. So there's all sorts of different generalizations and variants of this type of problem. But I'm going to stick to the one that I've already talked about, where U is essentially in the field. I'm controlling everywhere. And I do have the solution known on the boundary to be my desired solution. So here's the simplest problem of this type, perhaps. You have this desirable y hat. You have this controllable body force U. So this is the body force. And now we have just a Laplacian. Okay, so U is the forcing for the Laplacian in the domain. This is for simplicity, but let's keep it as this Dirichlet boundary condition. And beta is some parameter, positive regularization parameter. So all I've done here is I've just taken L is equal to the minus the Laplacian, the positive definite operator, right? That's the point. Here's the same problem. When I approximate this, so if I do finite elements, then that means essentially I choose a basis, I choose a space. And then I want to find some coefficients relative to a basis for that space for both the state and for the control. They don't have to be the same space, but again, I'm being simple here. I'm letting them be the same space, and I want to determine these vector coefficients that make these linear combinations, right? And then my problem is, well, hang on a second. If I want to do this minimization, the first norm was just the L2 norm, so I'm going to get a gram matrix, basically. This is the gram matrix for my space, for my basis here. The gram matrix being the ijth entry is the inner product of phi I with phi j. And so that's this term. And I get a term that's linear in y because there's a y with y hat. That's the cross term there. And then I get a term which just has y hat in it. And that just gives me a constant, so I don't worry about that when I'm doing optimization. And then out of the regularization, here's the regularization, I get again a gram matrix because I've chosen the same basis for these coefficients on the control. Right? So that's my optimality criteria. And here's my constraint. That is, I must solve the differential equation. And the differential equation, this is the discrete minus Laplacian. Right, so this is k, y equals m. these are explicitly these two matrices. The engineers call this one the mass matrix, and they call this one the stiffness matrix. But essentially, one is the discrete Gramian in L2, and one is the discrete Gramian in the energy in the product. But it's the discrete Laplacian. That's all you need to think about. Okay. So for such a problem, we can build a Lagrangian. We have the cost function, and then we add lambda, which is the Lagrange multipliers, and we add the constraint, which is the PDE. We apply the conditions of stationarity, and we get this saddle point system here for our state, our control, and our Lagrange multipliers. And this is a saddle point system because if you just take B as K and minus M in this piece, in other words, you block this matrix in this fashion, then A is like this, and you have the usual saddle point form. So I suppose it's not surprising that these problems turn out to be self-adjoint, because really you're optimizing and you're looking for stationary conditions. So here's a little observation that one of my students, Malcolm Murphy, came up with originally, then Jean Golub at Stanford, and I myself wrote the paper. And it's just a very simple observation really by now that if you have one of these saddle point systems, remember what I really need when I want to solve this is I need some approximation. So this isn't a function approximation, this is an approximation of an algebraic object, a matrix, right? And that approximation, I would ideally like to have few distinct eigenvalues. If I have that, I get very fast convergence. So our observation was if you take this matrix, and we asked the following question, if you take A and 0 and 0, what should you put in this corner in order that you achieve the best possible thing you can achieve for this problem, if you like? And what we discovered is that if you choose S to be this shear complement matrix, it's called the shear complement. I'm not saying it's practical to achieve this, but it's just a theoretical result at this stage. If we can find S, this matrix here, then using this as our preconditioner for this matrix problem yields us 3 eigenvalues, precisely these numbers, 1 and the golden ratio, and then 1 minus root 5 over 2, half minus root 5 over 2. If you make it triangular, then it actually has 2 distinct eigenvalues, plus and minus 1, or you could even get 2 eigenvalues of 1, but then it's not diagonalizable. But why is this important? Well, it's only important because actually here I have a candidate for an approximation. Because if I was to choose this, minres, or gmres in the second case, but let's say minres in the first case, would converge in 3 iterations. So that's pretty fast convergence. I don't mind 3 rather than 1, right? And I've just got to solve problems with this. And this is block diagonal, it's a little easier. What we do, in fact, is we approximate A and we approximate S, hence these hats. And then we can show very precisely that we get 3 or 2 clusters of eigenvalues, and we still get fast convergence of order 10 iterations now. When I say 10, bear in mind that in these expansions, which I very mildly put like here, right? These vectors are usually enormous. N is usually, millions, right? So 10 is pretty small, right? So that's a candidate. So in our problem, we know what B is, we know what A is. So what is this shear complement? What is S, B, A inverse B transposed? And so here it is, K minus M, that's B, and this is A, and this is B transposed. And you just multiply it together and you find it's exactly this. And this is the thing we want to have or approximate. And so I put this second term in blue because K, remember here, essentially is the differential operator. This is just a Gram matrix. This just tells me something about the space I'm choosing. Essentially, this is a nice matrix, a harmless matrix. It's very easy to deal with. Whereas this is really where my differential operator turns up. Here and here, it's adjoint. And so one first idea is, well, okay, why don't you drop this term, especially if beta is sort of large, then this term's pretty small. If it's a nice matrix times a very small parameter, well, this looks like a good approximation. And so then one has to solve this problems with this operator here. Another thing you can do, and this is due to my former student John Pearson, is you can, well, this again is exactly equal to this quantity, which has now got a root beta in it. If you take this, these are essentially like Helmholtz operators. But they're sort of nice Helmholtz operators because you're adding 2 positive definite problems together. And so this we call, well, the first term minus 2 over root beta kappa plus S2. And what you're interested in is, well, what are the eigenvalues if you do this? For S1, you can show they look like this. So H is the mesh size. So this can be very small. So that's really not a problem here. It's the fact here that if beta gets small, this can get large. C is a constant. With S2, and this is really rather the importance of John Pearson's result, if you do S2 inverse with S, that's the exact S here, the eigenvalues are between 0.5 and 1. So these eigenvalues are highly clustered. And it's for this sort of problem we can get extremely fast convergence. We can describe that fast convergence very precisely. So you can choose S equals S1. I shall actually show you some results with S1. If you have small beta, you can choose S equals S2. You have to solve these sort of Helmholtz problems, but they're nice ones. They're somewhat to positive definite operators. They're not scattering problems. Okay, there's also a nice paper, I should say, by Joachim Schöbel and Walter Zulner from Austria. So here's, if you just take S1, the preconditioner is this. This is just the block diagonal. What are the eigenvalues of this? This is what will determine my convergence, and you can write down bounds on these eigenvalues. There are lots of eigenvalues of 1. That's nice. You can prove that. And then there are eigenvalues, and these are a little complicated. What I put in blue is what you would have if you did it exactly. So you see here the golden ratio again, like I had in my previous result. Alpha 1 and alpha 2 are constants independent of H in these results. You don't need to look at the detail of that. Here's the picture. The eigenvalues are either 1. This is for a very small problem, so we can actually compute the eigenvalues. Or they're in this, I've drawn 2 parallel lines here. They must be between these 2 parallel lines. That's what the theory says, and they must be between these 2 parallel lines. And you can see essentially these parallel lines become a single line, and therefore you get the 3 eigenvalues, 1 plus root 5 over 2, and half plus root 5 over 2, and a half minus root 5 over 2, when you actually do the approximations exactly. So in other words, this theory is very descriptive. You essentially have 3 eigenvalues, or very tight clusters. So these eigenvalues are between 1.61 and 1.62 or something. But they're so clustered that it's very easy to do a polynomial that's small there by putting a root in there. And that's how my Krylov method works. But these things are still expensive, right? In the sense that we've got to solve differential equations and adjoints. So what we do is we just do approximations. So m hat will approximate m and k hat will approximate k. And then we get a precondition that looks like this with these hats on instead. And this is obviously some approximation of the Scheer complement. And the important subtlety here, actually, which it caused me more grief than it should have done. It took me longer to work out and to really express this, is that if you have a good approximation k hat for k, good in the sense I'm talking about, that it's spectrally very close, that the eigenvalues of k inverse k hat are quite close to 1, right? This would be a good approximation. They can be essentially quite close, and then this doesn't not necessarily approximate this essentially square of the matrices. It's just not true that a good approximation for a single operator means that the square or the normal equations is well approximated. And there are further conditions which you need. This is explained in a very nice paper by Dietrich Bryce and Peisker in 1986. And I've just written a small paper on this to add a little more to this story. Anyway, the conditions are satisfied in this case, and we can verify that. But it's a subtlety that's one of these things that takes you a long time to unearth. Sort of thing. So here's our idea. We are approximating these mass matrices on the diagonal and this k hat and the k transpose hat in this approximation to the Murphy-Golub-Wathen result. So what do we do for M? As I say, it's a nice matrix. This work was done actually with Martin Stoll, and he decided to use Chebyshev polynomials of the 20th degree, which is really, really overkill. But nevertheless, that's what he chose. That means you're going to do 20 iterations where D is just the diagonal of a matrix. So this is trivial. And this is Chebyshev. This is a classic method from the 1940s. And well, RK represents this guy, the operator, which is minus the Laplacian. And so when we have things like the Laplacian, well, Fortunately, there are many, many people who've gone before us. These are the people whose shoulders we stand on top of, that have worked on solvers for things like the Laplace operator. And in particular, there's a very large amount of work in the so-called area of multigrid. So if you know what multigrid is, fine. If you don't, then all you've got to think is that this is a method which is essentially a golden bullet for this type of problem. It's essentially a very, very efficient method for a particular type of problem. I'm not saying it's general, that it solves all problems, but it's a very, very specifically well-tuned method for these problems. There are geometric varieties of this method. That's what originally was derived and worked on by people like Wolfgang Hackbusch. And there are algebraic multigrid varieties where you don't need to know anything about the actual grids, you just work with algebra. And we've used a particular routine from the so-called HSL library from Rutherford Lab by Boyle, Mikhailovich, and Scott. So this one is called PMG, and this one is called PMG. And this one was one that we programmed in MATLAB, and this one is one that was actually programmed by some people who really knew what they were doing. This one should be slower, you see, because essentially it doesn't use as much structure as this one does, but that's not exactly what happens. So we do 2 cycles of these multigrid routines, and that's it. So here's an example problem. It's just a simple problem. Take the unit square or unit cube. Take a y-hat that looks like this. This is in the unit square. In other words, you pick up the corner. I mean, it's just chosen like this. It's not. It could be arbitrary, but anyway, we chose something that looked like this, which is actually quite 0 around the rest of the square and comes over the corner, correspondingly in three dimensions, which I can't draw. And we have the Laplace equation, Poisson equation constraint. We want to match the boundary conditions. We choose a value of the regularization like this, and we try and solve this problem. And so I'm not going to show you, I'm sorry, I hate to show tables and so on, but I want to show you trends, that's all, in things. So H is just the mesh size. So it goes from like a quarter down to 2 to the minus 9. That's the 1 over 2 to the 9 is the mesh size that we have in this mesh. 3n, 3 because we have 3 fields. We have the state, the control, and the Lagrange multipliers, and they're all essentially the same dimension here. So 3n is the size, the dimension of our problem. So this one was only 27 by 27, right? So this is not a big matrix. This is not difficult to solve. But this one's 783,000 by 783,000. Again, it's not difficult, but we're doing these in MATLAB. So this is actually, quite big for MATLAB, really. This is what happens if you use backslash in MATLAB. That is, if you ask it to do Gauss elimination. So there's a very standard technique. If you ask it to do Gauss elimination, it's utterly trivial for a 27 by 27 matrix. And it just simply runs out of memory on our computer that we're working on for this size of matrix. But actually, I was quite impressed. It went up to 200,000 before it ran out of memory. These are the times. But this doesn't fail because of time. It fails because the computer just doesn't have enough memory to store all the fill. These are our results with our method, the MinRes method, this iterative method. You can see it's not competitive for 27, who cares? Nobody's needing to worry about solving 27 by 27 matrices, but actually it's quite competitive when you get to here. These are the number of iterations, so this is 11. In the perfect case, it would be 3, right? But the important thing you can see is this is essentially independent of the size of the problem. And that's what we want to see. And we can still solve this problem. These numbers scale. This is in 2 dimensions, so these numbers scale by about a factor of 4. You can see 419 is about 78. So this should go to about 60. It goes up a little bit more, but not so much. But the iterations stay constant. So this is the algebraic multigrid method, and this is the multigrid method. This one should be quicker, but here's our coding. It's just poorer. It's a poorer implementation. They work so hard on the implementation here that actually the poorer method is better, but these both work. There's the state as it happens, and there's the control for the 2-dimensional problem. Okay. This is the 3-dimensional problem on a cube. And you can see here, I don't go to such big grids because I'm already up to the same sort of size problems as I had before, 750,000, when I get down to 2 to the minus 6. So this is again 3n, that's the number, the dimension of my problems. And this time backslash, well, it gives up much before this. Just because these matrices have more connections. There are more entries further away from the diagonal, so Gauss elimination just struggles more. And these run out of memory much quicker. Whereas these methods still work. So the factor is now about 8, because every time we halve the grid, which is what we're doing here, it goes up by a factor of 8, because 2 to the 3 dimensions. And so, yes, it's going up by a bit more than that for sure here, but the iterations is still pretty constant. All right. And this is again the multigrid method, and this time it does actually just win here. Just to show you the difference between the approximations I called S1 and the approximation of John Pearson I called S2. So this is the one where the eigenvalues are between 0.5 and 1. And here you can see that all the numbers, these are iteration counts, for every beta and for every mesh are essentially of order between 10 and 20. Whereas if you do the S1 thing, you can see that as beta gets smaller and smaller, then these terms in 1 over beta come in, and you can't expect to do so well. So that sort of mimics what the analysis says. Okay, let's see how am I doing. Okay, so I just put in some results when I have some bound constraints. So this is where I say we do this active set strategy. And really all I've done is the same problems here, the same sizes. This is the number of PD solves. Essentially, this bound constraint, I have to do some kind of nonlinear outer loop, you know, like Newton. It's not Newton, in fact, it's just pretty simple, this active set outer loop. And really what I'm trying to draw your attention to is that this is essentially the number of multigrid cycles. That's the sort of measure of the work here. The multigrid cycle is the work. One multigrid cycle is like the major piece of the work in each of these iterations. This is the number of multigrid cycles just to solve the unconstrained problem. And this is the number of cycles here to solve the constrained problem. And this is the number of outer nonlinear iterations. And so you can see it goes up by about a factor of 5. The energy in the unconstrained must be smaller than the energy in the bound constrained, as you'd expect. That's what happens. Here's the bound constrained problem. So the control is fixed between a surface down here, and I've cut off the top like here. So this is my U hat. I can't go any higher than this, and this is my U bar, which is this curved surface. And so the control lies on this surface some of the time and on this surface some of the time, and it takes this shape in between. And the state looks like the thing at the top for the two-dimensional problem. When you do state constraints, so this is the Murray sheet, I've not even put numbers in for that. Interesting thing here is this is the control, and you see this here. Well, the thing is, the control stops pushing when it's hit the bound. So this piece here, where essentially the state has hit the bound, means that there's no point in your control trying to lift it up, because there's nowhere it can go because it's hit on the constraint. So these are sort of interesting things. Okay, so that was our simple problem with the Laplacian. But people are really interested in solving other things than the Laplacian these days, typically. And well, you can conceive of this problem. So I introduced the Stokes problem as a saddle point problem. So here's the Stokes problem that I introduced before. And here's a corresponding control problem, or if you like, a PDE-constrained optimization problem. So you could have a y hat, that's just like before. You want your state to be something. You have an idea of the ideal flow, the ideal velocity. And here I put in a p hat. You may or may not have this. You have an idea of the ideal pressure. More often in these problems, you have some upper bound on the pressure and some lower bound. Lower bound is not so crucial, but an upper bound on the pressure. That is, you're not prepared to have pressures that are too high. Right? You don't want things to escape too much. So more often than this, you actually in these problems have constraints on the pressure, just bound constraints. And then here's our control. And here's our problem. I mean, we still have conservation of mass. So this is it, not going to change from 0, right? It's not that we're going to introduce mass or anything. We can't do that. We can't control the problem that way. But we can apply forces to the fluid. So for example, one example where you can think of this is, and it's actually done, is when you're melting aluminium, when you're melting bauxite mineral into aluminium, you do this with huge electrical devices, with a big anode and a big cathode, and you melt the stuff in between. And then what you do to control this, because it now becomes a magnetofluid, is you put on an electric field and you steer this fluid. And that's exactly one of the things you can think of as this is the steering force, the body force that we apply. That's one example. So We want to minimize this. This is our constraint. We can do mixed finite elements for the Stokes problem, exactly as I indicated before, to give us this sort of problem. You can build the Lagrangians. You can make the cost functional with the Lagrange multipliers. And then you can put down the stationarity conditions. Become more complicated. But essentially, if I was to draw a line along here and a line down here, this is a saddle point system with A in that corner, B down here, and B transpose up here. And there's still a zero matrix in this corner. So it's still of the right structure. It must be. It's an optimization problem with the constraint. And here, this is the body force, this is the velocity and the pressure. This is the control, which only acts on the momentum equation, as you've seen, only on the velocity. And then there's the Lagrange multipliers for the velocity and for the pressure. So you can solve these problems. You've now got to worry about the shear complement, which looks like this. You can do essentially S1 or S2, exactly as we did before. We can use Chebyshev for approximations of these mass matrices. They now might be different mass matrices for the pressure and the velocity and the control. Because typically when you solve these problems, you have to use different spaces for the pressure and the velocity. For those who know about this, this is all to do with the Bush-Cabrezzi stability. But if you don't, that's fine. You know you have to do this. And then you have to do two Stokes approximations, which are this K and K hat in the previous problem. And so the Stokes preconditioners look like this. You approximate K. Again, that's viscous terms. That's going to be a multigrid operator. And this is a mass matrix. That's an easy thing to approximate. Again, we'd use Chebyshev iteration. Then we use multigrid cycles for the scalar Laplacians. So there's various references here. And you get, anyway, symmetric shear complement approximations in this area. You see what I'm trying to say here, right? That this is a much more complicated problem. And I don't want to, bore you with what exactly it is. It's a more complicated problem for sure. But essentially what it's got in, every M is essentially a nice matrix. It's a gram matrix on a space that I choose. And I know how to approximate that extremely well. And every K is just a block diagonal set of Laplace matrices. So here they are in 2 dimensions. There's 3 of them in 3 dimensions. So this matrix essentially looks more complicated, but I know how to approximate this, and all these things I know how to approximate. And that's what I'm going to use, those same approximations in this more complicated problem. That's really the point. And when you do that, you come up with these shear complement approximations. And here's just an example. This is a so-called Q2, Q1 mixed finite element. That's essentially the simplest element. People would call it Taylor-Hood in the people who know about these things. But don't worry about it. It's essentially the simplest element you can choose. I'm going to use 4 algebraic multigrid cycles to approximate things. So that means I go through my grids 4 times, basically. I'm going to use the 20 Chebyshev iterations again for the mass matrix. Here are my mesh sizes again. For simplicity, just half the mesh every time. These are the number of degrees of freedom going up to about 420,000 this time. This is the number of iterations to solve this problem. So it's not 3 any longer. It's not even 10, but it's still 30. Right? And 30 is not bad when you've got a problem of this size. And if you double it, I mean, that's why I haven't doubled it. If you double it, well, what's the next one in this table? It's about 34 or perhaps 35. That's really what an engineer wants to know. How do I solve this problem? Can I solve this problem? And if I have something that's growing fast, the danger is I simply can't solve it at some stage. Whereas with this sort of guarantee, I can believe that this problem is solvable. This is actually CPU time. I think, I was going to say on this machine, but I think it's not this. I did these computations when I had an older Mac than this. These are not supercomputer computations. They were done on a laptop. And these are the CPU times in seconds. So I have to wait 300, this is about 5 minutes, right? For this problem, to do a Stokes control problem. So what I'm saying here, it takes 29 iterations to solve the Stokes problem by itself for this type of element, but only 1 algebraic multigrid V cycle for each iteration. And so, well, it takes about the same number of iterations here, but if you work it all out, it's essentially solving this control problem. It takes about 10 times more work, that's time and memory, than a single solve of the PDE. this is what I sort of wanted to see when we started out on these problems. Let's say we started off solving PDEs, and now we're sort of solving the PDEs as a part of this overall optimization problem in design. And if you can solve the problem of a design, and it takes only 10 times more work than actually solving an individual problem, this is, I think, quite a good gain. When I first started solving PDEs and I started working with people actually in the nuclear industry who were trying to compute flows of coolant in cores, in reactor cores, they were getting these things and they would do all sorts of things like, you know, do experiments like at Chernobyl in the computer, though, right? And not in practice. And to see, you know, what were the safety critical scenarios for this sort of, you know, the coolant, when the coolant couldn't cool down the reactor and you got these very dramatic, dangerous effects. And so actually they were amazed when I showed them, actually, you can say, well, why don't you put some optimality criterion? And that might be, you know, minimizing the pressure in the reactor vessel or something. You can solve it in 10 times as long as you could solve one of these problems. They're slightly amazed. They think of this as an enormously more difficult problem. Here's another example. When Airbus designed the A320. So this Airbus essentially sell more airplanes than Boeing these days because they optimize the wing shape. They use this sort of technology, which Boeing had only done in a wind tunnel. They never optimized the wing. They just built a wing and put it in a wind tunnel and make sure it had enough lift. So this is why if you fly on an airplane, you look on a 737, when you fly on a 737, there's all sorts of little rows of little things that stand up off the wing. Those to align the flow across the wing because it's not optimized. If you go on an A320, the wings are completely smooth because you don't need to do that because it's optimized. That's a matter of a lot of fuel and therefore millions and millions and billions of dollars. That's why Airbus sell more wings. They optimized. But it should be said when you, and the French did this, I should say. There's nothing to do with me. This was done by Pirano and people like this. This is a very important application of optimization of PDEs. The PDEs in that case were aerodynamic flow. But it's what's interesting is, of course, when they started doing this, they started to get wings that were infinitely thin in their optimality. So, you know, so they hadn't put in enough constraints to say these things must actually be buildable. You know, you must actually be able to make these things because they hadn't just put in the constraints. But that's not a criticism. That's just you know, they were doing this against the backdrop. Finally, and I will stop quite soon, I wanted to say a little bit about time-dependent problems. Okay, so the simplest problem I can go to that's time-dependent is, in fact, instead of the Laplacian, let's go to a problem of heat conduction or a parabolic problem, linear parabolic problem. And we're interested in the evolution of this equation. Here's the control again. This is heating in this case, if you think of this as being the heat equation. In some domain in space and then some interval in time. And the boundary conditions, well, I've chosen y equals 0 on d omega for simplicity. And I've got some, of course, now some initial condition like this. And the big difficulty with time-dependent problems is that you've seen I need k and k transpose. Well, k transpose is essentially the adjoint operator. It's a discrete representation of the adjoint operator for this differential equation. And the adjoint of this guy, as those of you who work in PDEs very well know, is this guy, whereas this is an initial value problem. This one is a final value problem. That is, you don't have initial conditions, you have final conditions. So this is the equation for your Lagrange multiplier, P, I call it here. And P is given at your final time, not at your initial time, as the difference between y and y hat at capital T. So when you want to solve a problem here, you've got to do a forward evolution and a backward evolution just to solve one instance of KK transpose. That's the sort of difficulty here. There's ways of doing that. They're not always terribly efficient, but I'm just going to show you some results. I'm not going to try and elaborate with more complicated things. We use backwards Euler. We use Galerkian finite elements. They would be pretty standard choices. We use trapezium rule for the time integral. Sorry, I mean, this is the optimality now has an integral over a domain. I put omega 1 and omega 2. They could be subspaces of omega. They could be omega itself. That is, you may control only on some part of the domain, but I put 0 to t, that is, you are trying to control over the whole of the time interval. This is, again, just one example of a class of problems. Okay, we use a trapezium rule to do this in time. And so the main issue now is to say that we have the solution forward in all these time steps, and the solution backwards. And so this K, what I've called K throughout, the matrix that represents the differential operator, is actually now all of these things where K is the discrete Laplacian and M is just this nice mass matrix. And these are the solutions of the state at the time step 1. So these are vectors, right? Y1 is the set of all state variables, the coefficients at time step 1. Y2 is the set of all coefficients of the state variables at time step 2, and so on. So this is now an enormous vector in itself, if you have lots of time steps. But essentially, you have the same type of problem. I've drawn it in great simplicity here. You've got this A, which involves 2 mass matrices. You have this B, which involves the differential equation and a nice matrix. And these things hide the fact under the notation that K bar, for example, this guy, is this enormous thing here that involves evolution over every time step. So these are huge dimensional systems, but essentially one can do matrix vector multiply. Remember, that was my first green spot right at the beginning of my talk to do MinRes. I must be able to do matrix vector multiply, 1 per iteration. That's the only way I visit my problem, is to do matrix vector multiply. So I have to do that. That's easy. And then I have to do these approximations of shear complements. It becomes a little more complicated, but essentially the same ideas apply. And the main issue, again, is the solution of shear complement approximations. And here's where your difficulty arises. This is a forward evolution, and this is a backwards evolution. Right. We employ multigrid. We actually here employ circulant. So we approximate in time by circulant matrices. Those are so-called parallel in time methods. And by doing so, we get results. You know, the biggest difficulty in 3D is you can't see the blessed solutions, and you can't see them here. I'm sorry, it's just some pretty pictures. But basically, you have a 3-dimensional domain here, and time. You have some desired state on the left, you have the state that you get, and some kind of control on the right. I could show you more detailed pictures to show you these do look sort of about right, but I thought it not worth it here. So I will finish there, and just I hope I've shown you that from going from solving simple quadratic problems with simple linear constraints, I have it all the time done linear differential equations. I don't apologize for that, because when you solve nonlinear problems, you often do linearization. That's the usual standard way to do it. So you've got to solve linear problems. And all I've done is tried to develop the methodology, which relies on these simple concepts from the solution of the Stokes equations, just the Laplace control problems, Stokes control problems, and now these time-dependent control problems. And you know, one can actually solve these problems. And I will just give you some references to finish. Thank you very much for listening.
Okay, all right. So one point that struck me, since we just taught this in the Cortona school. So when you have the block triangular matrix, you said I'm going to put the positive Schur complement in the 2-2 block. Right. That gives me 2 eigenvalues, but I could get 1 eigenvalue, but it's not diagonalizable. That's right. In reality, of course, diagonalizability doesn't really have much of an impact. Of course, neither does having 1 versus 2 eigenvalues in practice.
Well, yes. But, I mean, the point is, even if you get 2, you can indeed get 2 eigenvalues the same. You can get +1 or +1. The minimum polynomial essentially is x minus 1 squared. And so the Krylov space is essentially the dimension of the Krylov space, and the speed of convergence depends on the dimension of the of the minimum, the degree of the minimum polynomial.
But in practice, does it make any difference?
So that's a deeper question than I can answer, actually, Michaela. There was some indication from some work by Mark Embry and his co-workers when he was in Houston that having the same eigenvalue was a better thing to do. I can't understand why it should be. I think it sort of, either way, you're going to get something which is feasible. It may be that you can do better with one sign rather than the other. But I don't know the definitive answer to that question, actually. I really don't. Yeah.
In practice, I don't think it makes a big difference, but maybe if one wants to explain the convergence behavior observed, one may be more conducive than the other. Okay.
I mean, so linear algebras, numerical linear algebra people, and I've talked to some extremely very well-known ones, Henk van der Vorst, who was at Utrecht. He steered clear of anything non-diagonalizable, just like it was the plague, right? He really thought anything non-diagonalizable was really nasty. And so he preferred to have +1 and -1, because then you've got two algebras, they're distinct, and they each have a one-dimensional invariant space, basically. But actually, I think it's becoming clearer that you do get structurally degenerate, that is non-diagonalizable matrices. As you say, you can perturb a matrix and make it diagonalizable. That's absolutely true. But when you're dealing with these structures, you structurally get out of these sort of preconditioners matrices which have this degeneracy. So it's not an artificial thing. It's not as if you're, I always thought when I was growing up that, people said things like, well, you can always perturb a diagonalizable matrix, a non-diagonalizable matrix into one which is diagonalizable with an arbitrarily small perturbation. And that's true. But nevertheless, there are problems that arise which, if you think of them as being nearby a diagonalizable matrix, that's sort of disingenuous. That's not really true. The point is that the degeneracy, the non-diagonalizability is structural there. It really is something that is part of the structure of the problem. So I'm dealing, one of the things I didn't say a lot about here, but just mentioned in passing, was this time-dependent problems, where we approximate with a periodic problem in time. And there you get very large degrees of degeneracy. You get very large Jordan blocks, if you like, in a Jordan canonical form. And that's a structural issue, which is to do with causality. That you can't expect to overcome the need to know a solution at the same time before you can know it sometime in the future. But you can do things which mitigate that, which actually change degenerate problems into perfectly diagonalizable problems, actually.
Want to ask a question or have a comment? If not, let's just thank Andy again for his talk.
Thank you.